Good morning. Thank you for your kind introduction. So it's my great honor to introduce the IVIM session, and the first time, in fact, in the history of the ISMRM meeting that IVIM has received this honor to be presented as an educational talk. So I have no conflict of interest to declare. So let's start with what is IVIM. So intravoxel incurrent motion refers to the translational movements which within a given voxel and during the measurement time present a distribution of speeds in orientation and or amplitude. This is very important to understand, and I put on red all the keywords that need to be present in order to consider IVIM. And this is what I presented 31 years ago in radiology. And of course, the first motion of interest is molecular diffusion. And what I'd like to point out, this is a simulation of water diffusion next to cell membranes and aquaporine channel. And this is the diffusion, simulation of diffusion. Doesn't work? Yeah, okay. So what I want to point out, diffusion is about looking at individual molecules. And the diffusion displacements we are considering is very small, 10 nanometers, so very, very small. So these are the very first images I got back in 1985, and I was curious to see that maybe this is diffusion, but maybe not. And then I had to consider that blood microcirculation might have an effect on a diffusion-weighted MR signal. In fact, if you consider microvessels in a tissue, especially in the brain, they are like randomly oriented. So if we consider now the movement of blood, no, not a single water molecule, but many water molecules flowing in the capillaries, now look at the difference in scale. Now we are about talking about 1 millimeter, but still we have a random effect. And at the end of my talk, I will talk about something new. Mechanical displacement within tissues might also lead to an IVIM effect, and this is the base for virtual elastography. So diffusion MRI, diffusion sensitive, is sensitive to not only diffusion, but many other IVIM effects. So now let's go more to the details. I go to the Einstein vision of molecular diffusion and Brownian motion. So water molecules, or any molecules, in fact, they'll travel straight, then they hit another molecule, then they change the direction. So this is how we get a random walk. And in his Ph.D. thesis, Einstein defined the diffusion coefficient as a product of the mean length for the molecules to travel free and the mean velocity. So these are the parameters we have. The velocity is about 100 meters per second, and the average length is about 10 minus 10 meters. This results in a diffusion coefficient, which is 10 minus 9, so basically 1 10 minus 3 in tissues. And so this is good for us, because if we consider that the displacement of the molecules, according to the Einstein relation, is linked to the diffusion coefficient, in 50 milliseconds, water diffusion will diffuse on a few micrometers. So it's a right scale to explore the tissue microstructure, and as you know very well, the idea is to add some diffusion encoding gradients in the MRI sequence, and we get an attenuation of the signal, which has this shape. It's an exponential of minus b. The b value is the weighting of the diffusion sequence, and d is the diffusion coefficient. So if you plot the attenuation of the signal versus b, you get this exponential. So that's very well known. This is diffusion MRI. Now look at blood microcirculation. Again, now we are not looking at single molecules. We are looking at a pool, a bolus, if you like, of water flowing in the blood stream inside the vessels. Again, we can identify the mean capillary length, so the segments where capillaries are straight, and the mean velocity. And at the time, when I wrote my thesis, I loved all the Einstein's work, so I decided just to do a copy-paste. So, but replacing L and V by those values now. So it's completely different. It has nothing to do with diffusion, but I use the same equation. Now the length is about 100 micrometers, velocity is about 1 millimeter per second, so I get a pseudo-diffusion coefficient, which is 10 minus 8. So this is how it started. And I use exactly the same equation, but replacing d by d star. And the signal now gets decayed very quickly compared to diffusion. So we are very lucky because d star is about 10 times larger than d, which means that potentially we can separate diffusion and IVIM perfusion. Also in tissues, we have to consider that blood is about a few percent. I put 6% as an example, but it could be 4, it could be 10. And if you add the two curves I just showed, so the pure diffusion and the pseudo diffusion, you get this dark blue curve, and this is the IVIM effect. So the IVIM effect is seen only at low B values as a deviation from what we have from pure diffusion. So basically, it's very easy to write the signal weighting. We have the diffusion part, and we have the IVIM perfusion part with the correct weight. If you want to be accurate, we have to consider that in the blood, water is flowing collectively, but there are also individual diffusion of molecules. So in fact, we should have also, because this is often forgotten, that we have the diffusion coefficient of blood to take into account. So that was easy. This is a basic IVIM model. So IVIM perfusion and diffusion. And again, this curvature effect. So how do we separate diffusion from perfusion now? From this curve, we can see that if we calculate the ADC, the apparent diffusion coefficient, as a log of the signal attenuation, we can see that we get different values depending where we are. If we use high B values, for instance, between 200 and 500, the IVIM effect is gone. We don't see it. It's completely crushed. So then we have the ADC, which is diffusion. Now, if we look at, if we take 0 and let's say 500, you see that the slope now is less. So the ADC obtained between 0 and 500, sorry, the slope is larger. So we get ADC, which is larger than D because it contains perfusion. If we measure now diffusion, the diffusion decay signal with the ADC between 0 and 250, we can show mathematically that the ADC is the sum of the diffusion coefficient, the IVIM fraction, so the fraction of flowing blood, divided by the B value here at the frontier. And this is how it was introduced, in fact, in my very first paper, as a 3 B value scheme. So one B value is 0, one, for instance, could be 250, and one could be 500. Between 200 and 500, you get diffusion. And if you now use the two ADCs, 0, 250, and 250 for 500, for instance, you calculate F. So F can be seen, FIVIM, as the intercept between the diffusion curve and the total curve. So this was shown in this paper that I introduced in 1988. I have to say that, so you have two B values, 0. At that time, it was 100 and 200, but doesn't matter. But the problem is that at the time, there was no EPI, so 8 minutes to get each B value. So it was a little bit long. In fact, that was the motivation to do it with 3 B values, because we had no way to do more at that time, given the time requested to get the images. To prove that, we use, I think, a cute model, which is a Cefadex beads model. So these are some beads which are porous. So water can go inside and diffuse, but water can also flow between the beads, mimicking the pseudo-random flow. So we use that, and I think I really consider it's a good way to check it. So this is from my notebook from 1986 or 87. Just to compare with this curve, I invert this plot, and this was what we could see. So this would be the pure diffusion. In the presence of flow, you see that we get a deviation here and with intercept. And we could show that, yes, in fact, we can measure the perfusion, so the flow of water with this method. So I don't see well, but I think it's maybe 1986. So this was the very first images showing diffusion and perfusion IVIM maps. And that was published in this paper showing the ADC total, the diffusion part here, and the difference with this IVIM, so the high perfusion part. And I was very happy. Tom Dixon wrote a very nice editorial saying that it was really a tremendous potential. Unfortunately, it didn't work so well because the technique was difficult. My very first attempt, in fact, my goal was to do fMRI with IVIM. Because I'm sensitive to blood flow, I was thinking at the time that if I stimulate the brain visually, I could see activation in the visual cortex, for instance, before BOLD. That was well before BOLD. It worked, but not so robustly. So I didn't publish those results. And in fact, very soon, BOLD fMRI, and first gadolinium DTPA fMRI, but then BOLD fMRI came, and there was no need to do IVIM for functional MRI. But I was delighted to hear a few years later the team of Alan Song, who showed that they could get brain activation maps with IVIM. In fact, it's working very well, but BOLD is easier to do. In fact, the IVIM effect has been used in the context of fMRI to kill, in fact, blood signal. So because of the IVIM effect, if you add some gradient pulses to a BOLD MRI sequence, you suppress the flowing blood, so you get something more related to what you want to see. So it's a trick, but just to say that IVIM is still interesting in the field of fMRI. So again, as I said, the problem with IVIM at that time, it was done at 0.5 Tesla back 30 years ago, and 10 minutes for each b-value, so there was no way it would be useful clinically. So I was provoked. In the very first, it was not the ISMRM, it was the ISMRM workshop at that time, and organized in the States a workshop on diffusion and microcirculation. And some people said they were not convinced. So they said they had T-shirts saying that diffusion, perfusion, confusion, MRI. But today we have this IVIM session, which means that finally we were convincing. And Bob Tuner, who I met at NIH, changed completely the story because together we developed this IVIM EPI sequence. So we could get images now in just a fraction of time, free of motion artifacts. So we could get many slices. In 1 minute, you could get 16 B values in one slice, or you can get several slices. The B values also were getting stronger because of the gradient system he provided. And we could see very well this IVIM effect now in normal volunteers. And you can see that we could estimate FIVIM. I'd like to point out something which has not been really looked at so far, is that we found anisotropy in the IVIM effect, something which now we would like to investigate more. I know some groups have done it, but there is some anisotropy that we should investigate. So yes, it works, and especially Luciani, and first Yamada in Japan showed in the liver that in 1999, it was the very first time after the 1984 or 5 paper work I have done, that they could reproduce the IVIM effect in the liver. Also, there were motion artifacts. But Luciani in France had very convincing results. And nowadays, we know that we can measure the IVIM effect in the body quite efficiently in the breast or in the liver. So the nice point also is that if we consider that contrast agents as our reference for perfusion imaging, we should be very careful first because some patients, especially with a kidney dysfunction, might get a nephrogenic systemic fibrosis, which could be deadly. But more importantly, I think now people are getting scared of receiving gadolinium because it has been shown that gadolinium deposit in the brain. Sometimes there is a full session on that, I think, on Tuesday morning. And if you have to repeat exams, for instance, for cancer patients, or you have pregnant patients, we might be slow or at least be careful about using contrast agents. And in fact, in EU now, they are considering to ban linear gadolinium chelates from clinical use. So that's why IVIM In fact, this is just to show the deposits of gadolinium in the brain after repeated injection, but you need only 3 or 4 injections, not more. So I think that, of course, Tom Dixon could not foresee that, but I think maybe he was right, that the potential is very high, not because of IVIM per se, but because it might be with ASL, the only 2 left without contrast agents. Now, let's get to something more practical. So this is the same framework with the diffusion, pure diffusion, and diffusion with perfusion at the beginning of the curve. First question, how many B values? So first, I said 3 is enough. It is true. However, we have to consider noise. So these points might be very noisy. So the first choice is to say, we have 3 B values, but we will do averaging at each of the 3 B values. And then we can get the FIVIM from the intercept and D. That works very well. But we might also say that, well, why not picking up many B values? And this is another choice, to collect many B values and process in 2 steps. One step is using somewhat high B values to estimate diffusion. And once we have this diffusion, we remove the diffusion part from the overall IVIM effect to get this pure IVIM perfusion effect. And then we have also many B values. Now we can estimate not only F, but D star. So that's a good point. The problem is, where is the threshold? Where is the border between pure diffusion and diffusion and perfusion? That's an open question. And of course, it's very important to decide. I just show here a simulation where I took one, so if you take the usual unit, it's 10 for D star and 1 for diffusion. And if you take, for instance, 0.8, 10 minus 3 for the brain and 2 in the liver, just an example, you see that if we have 250 seconds per millimeter square, so right here, in the brain, the perfusion part is only 0.5%, so it's really negligible. But in the body, in the liver, it's 3.5%. It's not so negligible. So the threshold here might vary depending on the organs you are considering. So for brain, low thresholds are okay, but in the body, you might have to consider higher thresholds. Then we have to look at the impact on the diffusion model to fit this part of the curve, and what is the impact on this model we use here. And I will show you, and there is also a poster by one of our Ph.D. students here, Dr. Liao. You will see that it's not trivial. So now we get a little bit more inside. So again, this is a basic equation I introduced earlier. And we have to keep in mind that in tissues, the Einstein model fails. Water is not free. Water is hindered by obstacles. So as a result, the diffusion attenuation is not a straight line. It's not a single diffusion coefficient. This is really an approximation which I have made very early on to simplify our life, but we know that today this approximation of mono-exponential diffusion is not right. So as a result, we have a curvature. So if we measure the ADC in a tissue which has no perfusion, no IVIM, right? If you take this curve here between 0 and 1,000, you see that you get a deviation from the diffusion because you cannot describe this curve with a straight line. That's clear. So if you calculate the ADC between 250, as I suggested, and 1,000, you see that we get an intercept here. So there is an IVIM effect. Also, I said there is no perfusion in this artificial tissue, just diffusion. So it is an artifact related to the fact that we use the wrong model for diffusion here. So there are many models available to take into account this non-Gaussian diffusion. But if we don't do it, if we use this equation, we have clearly an overestimation of FIVIM. We can see even IVIM effects where there is no perfusion, which is, of course, a big problem. So this should not be used if we consider high B values and non-Gaussian diffusion. So several models can be used. I suggested, for instance, here the kurtosis model, or we can use a two-compartment bi-exponential diffusion model. But again, here you may consider it's bi-exponential, but now we are, in fact, we have a three-exponential model. One exponential for diffusion, for perfusion, I'm sorry, for IVIM, and here we have a bi-exponential model for diffusion. But again, today I think that the kurtosis model is more popular. Second pitfall, noise again. We are still talking about the diffusion part here. So this is a real data set, okay? And I do exactly what I suggested. So we take 250, we take this part, and we apply now the kurtosis model. Good. And I look here. I remove the diffusion part and see what I get. A negative IVIM effect. Why? Well, the problem is that this curvature we have here is not from non-Gaussian diffusion. It comes from the noise. In fact, there is a noise floor here. As you know, the Rishon noise floor, because we use the magnitude of the signal. So the signal can never go to zero. It will stabilize at a level here, which I call, as everybody calls, the noise floor. So this curvature here cannot be handled with the kurtosis model. Otherwise, you get a negative IVIM effect. So what you have to do, and now it's quite clear, we have to correct the signals for this noise floor effect. So there are several ways. We have introduced one. So basically to look at the signal which is in the noise, or at least to ignore the points here. So if you process now the signal properly, so you have the IVIM effect, the kurtosis diffusion model, and the correction for this noise floor, then if we remove the diffusion part to the overall signal, we are happy to see that we get the positive IVIM effect. Again, this is a normal, this is a typical tissue. It's not a simulation, it's a real data. So you see, handling, the message here is that if you mishandle high B value signals, you get wrong results at low B values. This is not intuitive, I agree, but we have really to be very careful about that. IVIM effect could be completely wrong if we don't pay attention to what happened at high B value. So we have to get the right model to consider non-Gaussian diffusion and Rishon noise. Otherwise, we might get something wrong for the IVIM effect. So now, let's take care of this part here. So I have introduced this idea of, from Einstein, a copy-paste from Einstein, so it's exponential decay. But this works, in fact, well if flows of blood changes direction several times during the measurement. So that means the flow should be not too fast. The capillary segments should be not too long, not too small, so that the blood can change several times. And that measurement times, diffusion times, are not so short, which is the case anyway in clinical systems. But back again in the appendix of this paper, I suggested a second model where the blood doesn't change segments because we are not in those conditions. So this was back in 1986, in fact. And I showed that in this case, in the extreme case where the blood never changes segments, but the segments are randomly oriented in space, we get another signal decay, which is, so again, we have the diffusion of blood in the vessels, but now instead of BD star, we have a sink of CV. V is the velocity of the blood, and C is like the B factor, but now it's a C factor, and it is a little bit different. So this model will work for faster flow, shorter segments, or short measurement times. So which one shall we use? Well, people have shown that, in fact, unfortunately, we could be right in the middle. So it's not really this one, not really this one. We are between the two. So models have been proposed, especially the Canon model, but in fact, it's quite difficult. So recently, Gabriel Fournet in our laboratory showed that, in fact, we did some simulation showing first that if the blood changes 3 times the orientation, it's enough to get an exponential shape. So that's good. Now, if we take this model with a sink decay, but we have a distribution of velocities, that means that the velocity is changing from one segment to another one, then because we have a convolution with the distribution which is Gaussian, we get at the end something Gaussian anyway. So the message here is that the pseudo-diffusion model appears appropriate in most situations, at least on clinical systems where we have long diffusion times. Okay, now something more complicated is to see, well, what's the link with microarchitecture. So what are we looking at? So this is an electronic photo I got of the capillaries, and we might think that maybe there are different scales of capillaries. In fact, some other groups have also considered in the past that there are different pools of perfusing blood which have to be taken into account. So recently, we looked at this, again, the signal attenuation now for IVIM, so remove the diffusion part. And yes, indeed, sometimes when we have very short diffusion times, we can identify a bi-exponential decay. So here we have compared mono-exponential, so E minus D star, with the bi-exponential for perfusion, again, not for diffusion, and the Cannon model. The Cannon model doesn't work so far, but we can see that with the bi-exponential fit for perfusion, we get better results. So this will be now the IVIM bi-exponential model, but the bi-exponential now is for the IVIM part. So there is a slow perfusion part and a fast diffusion part, which becomes visible only with very short diffusion times. With clinical scanners, this is usually completely crushed and you don't see it. The other question that we all face is how could we link IVIM parameters with classical perfusion or ASL or DCI? In fact, this was a question that was provoked by Mark Henkelman back in 91 or 2. Does IVIM measure classical perfusion? And with Bob Turner, who responded the link between IVIM and classical perfusion. So let me show you. It is also quite interesting. With classical perfusion, we consider that we have a delivery of nutriments, such as oxygen and glucose or tracers, to tissues. So it's a functional definition. And the key parameters alike is blood flow in milliliter of blood per minute and per 100 gram of tissue. With MRI, what we see is a transit of blood. It's not the same concept. And the parameters that we usually have is the blood volume, which is like FIVIM, if you like. And with ASL, we look at the blood which is flowing through the slice of interest, while with IVIM, we look at the blood which is flowing within the voxel, so within the slice. So we should be also careful when interpreting ASL and IVIM data. So we are not looking exactly at the same phenomenon. But let's go back to classical perfusion. So people doing perfusion measurement with contrast regions or tracers, they want to see the blood flow, and for that they use the concept of the mean transit time, which is obtained from the surface of this curve when you look at the contrast uptake over time. So we cannot do that with IVIM, but we know the geometry. The mean transit time can be defined as a time taken for the blood to flow for a complete capillary segment between arteries and veins. So this is an anatomical factor that is very stable. So if you replace now in this basic definition the velocity with d star, as I showed in the beginning, we get that we can estimate blood flow with IVIM as this very simple equation. So blood flow is linked to the product of FIVIM times d star. And you find in the literature very often that Fd star is an index of the blood flow. The problem is d star, and I think Sigmund probably will talk about it, is quite tricky to estimate, and I think that's an limitation. Okay, and very quickly now, because time is running out, I'll show you that we can also, but again, just for stimulation, looking at the distribution of velocities within a vessel now, not capillaries, we have also an IVIM effect, which can be used to recognize vessels and obtain angiograms based on IVIM, so no contrast agent. And the second point, but I will be quick because I will give a detailed presentation of that, is virtual elastography. So the idea is to obtain maps of the elasticity of tissues from diffusion, not using any mechanical vibration. And I'll show on Thursday that it works well. But the points I'd like to make today is that if you have waves propagating in the tissue, if elasticity is low, in the background, for instance, you get some dispersion of phase, which is not big, so which is very big, I'm sorry. So the signal will drop a lot, and because of this IVIM effect. If you look at a tumor in a lesion, you have like tumors usually have very high elasticity. You see that dispersion of the mechanical displacement is much less. So we get a contrast based on this IVIM effect, which has nothing to do with perfusion, is linked to the mechanical dispersion. And we can get a new kind of contrast, which is IVIM-based elastography, if you like. But again, as I will show on Thursday, there is no need to use mechanical vibration for that. So we can get elasticity IVIM contrast like that. So to conclude, so IVIM refers to the translational movements which occur in a voxel, could be diffusion, perfusion, and shear wave propagation. In order to estimate the perfusion from that, we can use a simple approach using 3 B values, but we have to consider the noise, or multiple B values, and one common approach is a 2-step approach. There are other ways, and I think Sigmund probably we'll talk about that with. And IVIM corresponds to this fractional flow of blood. In order to get proper estimates, we have to handle high B-value signal very carefully, such as non-Gaussian diffusion and Richer noise, very important. The potential of IVIM is high because now people start to be afraid of using gadolinium complexes in fear of deposits in the brain, and the FDA has cleared IVIM as a tool for clinical applications, and Olea was the first to get this approved. And in the future, we might consider also virtual elastography based on IVIM effect. So I'm running a little bit late, but I thank you so much for your attention.